Okay, so welcome. My name is FX, and this is Fabs, and we happen to work at the same company. And since I'm his boss, I get to steal the fame from his talks. So I can give the first slide, and then he has to do the work, which is good. And I'm also responsible for making him work on stuff. And so we had a partial disclosure this year, quite similar to Dan Kaminsky's DNS partial disclosure approach. And Dan's case was special. Oh, sound system. So Dan's case was special. It was the first time that he tried something, and he did it in his own way. But the next levels of partial disclosure were interesting because now someone steps out and says TCP is broken, but we don't tell you where it's broken. And well, there are two aspects of it if you're working in security. The first is you don't know how responsible the other person discloses this bug, and you don't know how much they care about it. So if you actually are not in the loop, you don't know what the bug is, but it's published, then your base of information says, well, the bad guys probably have it already, and the good guys are not getting off their dollar body bar to fix it. And so, what are we going to do? So that's a bad situation if you need to tell other people, which is the second point, is there are many people in this world that rely on you as a source of trusted information. So they read somewhere online, oh, TCP is broken. They go like, TCP, I think we have that. And then they call you. And, well, they expect you to give them a decent answer. And if the answer is, don't know, that's actually not really good, because that makes them go panic over something that they shouldn't, or makes them ignore something that they should panic about. So that is a problem, and the discoverer, the original discoverer that followed partial disclosure might actually not care about all that. And then it actually is quite useful to have a research department and like small half Japanese people that you can throw at problems and go like, break this. And here he goes, Fabian Yamaguchi with his discoveries on TCP.
Okay. When we first started our research on TCP denial of service attacks, the initial question was, what is it that Outpost 24 actually discovered? But that soon made room for a more generic question, which is there anything in TCP at all which counters denial of service attacks? And in this talk, we want to justify our answer, which is basically, well, there's not much. And apart from that, you know, this has been really exciting. So I'm trying to motivate you to get into this spec hacking because it's really fun. Okay, so first of all, what are we talking about? Denial of service. Well, that basically means that what we want to do is either make a service unavailable, or make the host unavailable which runs the service, or make the network, the complete network, unavailable. And if we look at the history of TCP, then we know it's developed somewhere in the 80s and as a military project. So of course, availability is a major issue. It's just that they've taken an approach to availability from a really, from the Cold War perspective, which is totally different from ours. So if you take a look at the whole protocol suite of TCP/IP, what you always hear is the so-called end-to-end paradigm and decentralization, which basically means that what they've done is they've moved the entire intelligence of the system into the end nodes, which basically means that if something breaks in between, that's not that bad. The services are still going to be available. Now, what they didn't think would ever be a problem is, teenagers in their basement who have access to the network and which could, create denial of service from within the network. So what they actually address is robustness of the complete system, and not so much attacks from within the network. So there are really no security features to counter this, none at all. Okay, so I hear you saying no security features. What about sequence numbers, source ports, stuff like that? We all know we can't just get into hijack a TCP connection because we're going to need a valid source port, we're going to need valid sequence numbers. But if you take a look at these concepts, you'll soon discover that source ports have nothing to do with security. Source ports were introduced to do multiplexing. That means you have several connections over one physical link. And sequence numbers are there to provide ordered data transfer, so that if you put A and B into the network, you actually get A and B in that order on the other side. Now in 2004, this guy named Paul Watson demonstrated a couple of attacks, so-called TCP reset attacks, and they very much show why it's a bad idea to rely on things which were not initially thought of as security measures to provide security. As a response to these attacks, what was done is TCP source ports were randomized. So this should ring a bell. We're going to get into that later. But they were not initially specified to be random. So this is not a security feature. And this is the kind of setup that he took a look at. The two hosts, the one up there and the one down there, they have a TCP connection. And there's an attacker which can reach both of the hosts. Well, he just needs to reach one, but anyway, he doesn't sit between the two hosts, so he can't really see what they're talking about. And now what he wants to do is he wants to reset the connection so that they can no longer communicate. So now you may be thinking, okay, so he needs a sequence number. That's like 1 out of 2 to the power of 32, but that's not really the case. He just needs a sequence number somewhere in the so-called transmission window, which is the amount of data which is currently out in the network. Now, the problem with this is really that if you take a look at what people are working on in TCP, then we want more performance over long-fed networks, which basically means something like satellite links, stuff like that, where you have lots of bandwidth, but it takes awfully long to get a response. So one thing they introduced was the so-called extension for high performance, and it allows you to increase the window size to a maximum of 2 to the power of 30. So that then leaves you with, 4 tries. Okay? So that's pretty easy. Well, you don't really have, you never have windows of that size, but you have windows of huge size in the core of the internet, BGP, where you have long-living TCP connections with huge windows. So that was a major issue, and the issue arises because there's really a clash in responsibilities here. The sequence number is supposed to just tell you what byte in the data stream you're looking at. It's designed to provide ordered data transfer, but people just assume that it's a security feature, which it is not. And now we add the high performance extension, and suddenly the space in which you need to guess becomes really small. But it took this guy to also convince us, to randomize UDP ports while we're at it. So, yeah. So let's just sum this introduction up with a nice statement by Stefan Hemminger, who is a major contributor to Linux TCP. He basically says on his blog somewhere, anyway, fast forward out of the peace and love decade and welcome to the modern internet with people trying to mess up TCP connections. This kind of attack from within was unfortunately not one of the scenarios that the initial internet designers considered. And it's been a bit of a problem since. Okay, so now we will have to go for some important basics, so bear with me. First of all, if you put a service onto the internet, what you want is that it can serve as many concurrent connections as your resources actually allow. But there's one unfortunate fact about this approach, because if you really do just handle things without any bound, then soon somebody will be able to exhaust your memory, which causes kernel crashes, and that basically means that you have to get up in the middle of the night and reboot your server, and nobody wants that. So what was introduced by implementers, and this is important, this is not in the TCP specs, was the so-called backlog. Okay? So the backlog was initially the number of pending connections that could be in the queue at one point in time. So once that was full, no more connections were taken to protect memory, basically. So this is kind of an artificial bound. And it's a problem because if this artificial bound is just a lot lower than the actual memory that you have, then of course it will be a lot easier to exhaust this the artificial bound. Okay? And now that Outpost 24 announced their vulnerabilities, there's been a lot of talk about, SYN flooding, the old style SYN flooding, and comparisons to connection flooding. And people talk about it like it's pretty much the same thing. All that happens is you send another ACK, and the effects are the same. And I want to clarify this issue because, you'll see. Okay, so this is the backlog that got SYN flooded. What you see here is it is the queue of pending connections, which means if you send a SYN, then you can create an entry in this queue. And you can also send an ACK, and then that will be an established connection. But what's important is, the gray blocks, the half-open connections, they are unknown by the layer 5 application, which may be Apache or something like that. So Apache is not yet able to retrieve these connections. So if you just fill the complete backlog with half-open connections, then the server won't be able to take in any more new connections. So this was fixed, and now we're looking at, one more thing. What makes this extremely attractive is that you don't even need the answer from the host, so you can spoof your IP address. So if somebody says, if somebody's attacking us, then let's just block that IP. You can't do that for SYN flooding, okay? And this is the backlog today, and it's very different. The backlog today contains all the connections which are fully established, but which have not yet been accepted by the layer 5 process. So this is important because the layer 5 process can accept these connections at all times. There are no connections which it does not know about yet. So here's the direct comparison. Basically, the point of all of this is that the impact of the attack for SYN flooding is the same regardless of service. But for connection flooding, it's actually your responsibility as an application writer to make your program resilient against connection flooding attacks. So there are a couple of things you need to watch out for. If you don't accept new connections fast enough, what will happen is that the backlog will be exhausted. So it will feel pretty much like a SYN flood. That's the same part of the system that's been attacked, even though it's a bit of a different backlog, really. And once that you have accepted these connections, there is no bound on them. Okay, so the backlog does not tell you that if you want to handle 5,000 connections or something for one host, then that's all your business. TCP has nothing to do with that. Okay? So what does that mean for you? Well, it means if you write a TCP-based service, you need to keep in mind that you will have to have a short thread of execution which handles accepting, so that you don't have too much code between subsequent calls to accept. And you need to place your own upper bound on the number of connections you handle, because TCP is not going to do that for you. And this bound, you can't just say, okay, 50 is a nice number, let's take 50. You actually have to look at how much memory do I have, how big can kernel buffers become, stuff like that. It's tricky. It's not that easy right now. I mean, I'm not saying that it's a good idea to have the application responsible for these things, but right now the application is responsible because the kernel is just not going to do anything about it. Okay? But there's one thing which you cannot counter on layer 5. Because at some point you're going to say, you know, I'm finished with this connection. Maybe even because somebody's flooding you and you're saying, I'm just not accepting anything anymore. And at that point, you give the connection back to the kernel, and it has to handle these things. Now the specs place no upper bound on how the timeout's supposed to be on these kind of, you know, finished connections. So what we found is that really the timeouts chosen are ridiculously long. Okay, so those are like 7 minutes, 11 minutes, stuff like that. Okay, so you'll just have lots of connections in FinWait 1, and you really can't do much about that. So that's one of the real effects of that you can do with connection flooding. And the TCB, which is all the memory that you need for a connection, must remain allocated. So this is valuable kernel memory that's allocated, okay? And also, you can enlarge ridiculously long, okay? Usually the timeouts that you have in FinWait 1, they're related to the so-called retransmission timer. Now the retransmission timer is related to the round trip time, and you obviously control the round trip time because you can just delay an acknowledgement as long as you like. So this is a line from Linux TCP where there's a maximum of 2 minutes for the RTO, and we'll probe several times, so you'll be stuck at about 16 minutes, something like that, for each of these connections to time out. And also you can enlarge the TCBs, so that's all the memory you need. Because if you took a look at SYN flooding, all you got was the minimum TCB. You just made the connection and didn't really complete it, and you had no chance to say stuff like, oh, I'm far, far away, you need to send lots of data at once, you need to queue lots of data, but with a fully established connection, we can actually do that. So this is exhausting memory with a shell script. It's really easy. All we do is we request a file from a web server in a loop, and then we kill it. We kill the program which requests a file, and we just don't send any resets or fins or anything like that. We just let the connection hang. And this is what you see. This is an SDOT and the size of the send queue, as you can see, in gigabit Ethernet, is like 4 megabytes. So you have 4 megabytes for each of these connections, which may be hanging around for like 7 minutes if you don't do anything to make that longer. Okay, so that's a bit of an issue. And also, it's not hard to pretend that you're in a gigabit Ethernet with the target. You know, you may be thinking, ah, well, this is just if you're directly connected to it. No, when we hack congestion control in a few moments, you'll see it's really no problem. And then there are implementation bugs which can help you increase the efficiency of these kinds of attacks. And this is really interesting because what we're doing is we're using different features of TCP, you know, to kind of attack each other. Now you've probably all heard about the flow control mechanism of TCP, and it allows you to tell the peer that you only have a buffer of like, whatever, 20 bytes left or so for new incoming data. Now what people often do when they attack machines is they say, oh, I have a flow control window of just 1 byte, and then things are going to be really slow, and you know, it's not nice for the peer that you attack. But now people think that if you use a flow control window of 0, that's pretty much the same as just any low number, but it's not the case. Because what happens is that the flow control mechanism goes into another state called the persist state. And the interesting part here is that this switches on the persist timer, which checks if you can send new data periodically, and switches off the retransmission timer. Okay? Yep, and those terms are mutually exclusive, I just told you. So you may find stacks which handle these connections correctly. So this is some partial disclosure for you, just to motivate you to work on these problems. And we have another related unfixed vulnerability. These are just implementation things. And I don't want you to walk out of here and think, oh, Linux stack, that's so broken. No, that's a really, really cool stack. It's just that, things go wrong and stuff. There's a bug that Fefe disclosed but on his blog, but nobody seemed to really care about that. There's a feature called TCP defer accept in Linux, which gives you the ability to delay the acceptation of new connections until after the first segment of data has arrived. Okay, but if you don't send any data, then you will have established connections which the layer 5 process cannot yet fetch. So it's SYN flooding all over again, and here's a little hint, Apache now uses this by default. Okay, for the last part, hacking congestion control. This is what I found to be really interesting. There's a mechanism in TCP which controls the amount of data that a TCP injects into the network at any point in time. And in the 80s, what they found out when they didn't have nice specifications on how to do this, so-called congestion collapses occurred. And this is a nice quote from the really most important paper ever published in congestion control, you could say. This is one of the first. And they're saying, in October of '86, the internet had the first of what became a series of congestion collapses. During this period, the data throughput from LBL to UC Berkeley dropped from 32 kilobytes per second to 40 bytes per second. We were fascinated by the sudden factor 1,000 drop in bandwidth. So this mechanism kind of matters, okay? So if you have the big pipe in this picture, then flooding the network is really not an issue. But if you have the little pipe, then you need to get the guy with the big pipe to flood the network. That's the basic idea. Can you do this? Yes, you can. So you're using the target's bandwidth against itself. That's a ninja, by the way. Okay. Now there are two mechanisms, congestion control, flow control, but in both cases, we are the trusted source of information for these mechanisms, okay? So this is basically how it works. One side sends data and we acknowledge it, and then they say, oh, okay, so you got that. Well, then I'm gonna try to send some more until packet drops occur, and then they say, oh, okay, this was too much, now we're sending a little less, okay? Trick number one, who says we can't just hide losses? Okay, so he sends data, we say, oh, okay, we got that. Sends more data, we say, got that. Sends more data, we didn't get it, but hey, we got that. Okay, so this, what this does is that the congestion window, which is the amount of data which is pumped into the network, just increased and increased and increased until it totally floods the network. Okay. So, and you can be even more nasty about this. You can also acknowledge before you even got the packet. This leads to the scenario where the host thinks that the round trip time is really, really small. So it's like you're in the gigabit Ethernet, just what I told you about earlier. So we control the round trip time. We control the round trip time samples which are taken. And now here's another nice quote from that really cool paper. A good round-trip time estimator, the core of the retransmit timer, is the single most important feature of any protocol implementation that expects to survive heavy load. Okay, but we control the samples. Okay, so all of this, this is actually known stuff. People have looked into this, but it's just that nobody cares that much. And this guy, Rob Sherwood, he actually wrote a paper about this and did lots of testing. And this paper is titled, Misbehaving TCP Receivers Can Cause Internet-Wide Congestion Collapse. And nobody cared. And then he actually wrote a patch so that they could just use the patch so that he'd be happy. But nobody applied it. Okay. So there are two ways of fixing this problem. One is really neat in that it's the nice way to fix the problem, but it requires to change TCP. And that usually isn't an option because then you have to change TCP stacks all over the world. You can't do it. Okay. This approach is that the receiver should not only say, I got the packet, but he should prove it by calculating a checksum over the packets that he should now have. Okay, good. And then there's another fix, the one by Rob Sherwood, and it's fully backward compatible, but it just randomly drops segments and sees if the other side says, oh, I got that segment, because then you caught him lying. The problem you have here is that it induces a minor throughput penalty, and TCP people don't like minor throughput penalties. Okay. I want to end with another quote by Stefan Hemminger. August 2007, somebody came up to the Linux kernel list and asked, you know, I just played around with this stuff from Rob Sherwood, and you know, it's kind of dramatic in a way. Are we doing anything against this? And here's the answer. Lastly, the patch looks like it could cause more problems. It probably will break some application and other non-attacking TCP stacks. For this case, in my humble opinion, we need to wait for more research. If you want to pursue the problem, it needs to go through the RFC process. So that's going to take a while. Okay, so here's a hint on what to try out next, because we've tried lots of things, but we couldn't complete everything, and you know, this is kind of also a call for you to do some research on these things. Flow control and congestion control are completely independent mechanisms. So what you could do is you could start a download, and then the congestion window will go up, and then at one point you say, I have no more bytes to receive more data, and it will hang there. Okay, then you do that a couple of times, and then you tell all of them at once, fire. Okay. Yeah, okay. And then there are also some things that you can do without even, you know, leaving the RFC. Because, as we just said, these congestion control mechanisms are fully drop-based. So if there's a drop, that means there's congestion. We should send less data. But it's possible that it's not a sign of congestion. We can actually create scenarios where we have drops even though there's no congestion. And I'm not talking about wireless. The shrew attack. This is also something that you will find on the internet, but nobody cares. Yeah, this is their logo. Anyway, yeah, it's a little mouse, and it attacks big elephants, so pretty similar to the picture that I had before. So here's a basic idea. With a normal TCP stream, segments that you send are pretty much equally spaced. You try to not have too bursty data, and sometimes the queue in a switch may be partially full, but sometimes not. But you know, that's normally what it looks like. But now what happens if you as an attacker just send the same amount of data, but in a single burst? What happens is that you fill the queue completely, and the next packet will just be discarded. Okay? Now the retransmission timer is extremely predictable because it's part of the congestion control scheme, and that's been completely specified in great detail. So what this means is that you could always send these kinds of data bursts whenever the retransmission timer sees if it can send data again. Okay, so you get the situation where you really want that file from the web server, and somebody really does not want you to have that file. In this case, a shrew attack can screw you. Okay, understood? I'm not sure. Okay, so there's a proposed fix from academia, and this is funny. They say, well, you know, we can't really, it's not specific packets that are attacking us or anything, but it's this periodic stream of bursts. So if we treat the incoming data as a time signal and then do a frequency analysis on this, academia, okay, then we should be able to see, we should be able to identify shrew attacks by their spectral properties. Okay, and then to be sure that everybody takes them seriously, it's like, you know, this is practical. We could use DSPs to implement this really efficiently. Now, if anybody ever implements this, we will show you how to break this next year. Thank you. Okay. Oh, so first of all, I want to say special thanks to Ethics, for getting us cool projects, and also special thanks to Bruns for working with me on this. And if you have any questions, I'm going to take them now.